Okay, thank you, Matthew, for the very kind introduction. Before we start building AGI, we need to ask ourselves the hard questions. What is intelligence? How can we measure it, benchmark progress? And what are the directions that we should follow to build it? So I just want to give you my take on these questions. And I'm going to start by taking you back to peak AGI hype, which was early last year. Do you remember what February 2023 felt like? ChatGPT had been released just a couple months prior. GPT-4 just came out. Bing Chat just came out. It was the Google killer. Anyone remember Bing Chat? And we were told that ChatGPT would make us 100x more productive, 1,000x more productive, that it would outright replace us. The existential risk of AI was becoming front page news. And AGI was just around the corner. It was no longer 10 years away, not even 5 years away. It was just a couple years away. You could start the countdown in months. And that was 1.5 years ago. And clearly back then, AI was coming for your job right away. It could do anything you could, but faster and cheaper. And how did we know this? Well, it could pass exams. And these exams are the way that we tell whether other humans are fit to perform a certain job. If AI passes the bar exam, then it can be a lawyer. If it can solve programming puzzles, then it can be a software engineer and so on. So many people were saying that all lawyers, all software engineers, all doctors and so on were going to be out of a job, maybe even within the next year, which would have been today. In fact, most desk jobs were going to disappear, and we faced mass unemployment. So it's very funny to think about it, because today the employment rate in the US is actually higher than it was at the time. So was that really true? You know, was it really what the benchmarks were telling us back then? So if you go back to the real world, away from the headlines, away from the February 2023 hype, it seems that LLMs might be a little bit short of general AI. I'm sure most of you in this room would agree with that. They suffer from some problems. And these limitations are inherent to curve fitting. They're inherent to the paradigm that we are using to build these models. So they're not easy to patch. And in fact, there's been basically no progress on these limitations since day one. And day one was not last year. It was actually when we started using these transformer-based large language models, so over 5 years ago. So over 5 years ago, and we've not really made any progress on these problems because the models we are using are still the same. They are parametric curves fitted to a data set of the Gaussian descent, and they're still using the same transformer architecture. So I'm going to cover these limitations. I'm not actually going to cover hallucinations because all of you are probably very familiar with it. But let's take a look at the other ones. So to start with, an interesting issue with LLMs is that because they're autoregressive models, they will always output something that seems likely to follow your question without necessarily looking at the contents of your question. So for instance, for a few months after the original release of ChatGPT, if you asked, what's heavier, 10 kilos of steel or 1 kilo of feathers, it would answer, they weigh the same. And it would answer that because the trick question, what's heavier, 1 kilo of steel or 1 kilo of feathers, is found all over the internet. And the answer is, of course, that they weigh the same. And so the model would just pattern match the question without actually looking at the numbers, without parsing the actual question you're asking. And same if you provide a variation of the Monty Hall problem, which is the screenshot right here. The LLM has memorized perfectly the canonical answer to the actual Monty Hall problem. So if you ask an absurd variation, it's just going to go right through it and output the answer to the original problem. So to be clear, these two specific problems, they've already been patched via RLHF. But they've been patched by special casing them. And it's very, very easy to find new problems that still fit this failure mode. So you may say, well, these examples are from last year, so surely today we are doing much better. And In fact, no, we are not. The issues have not changed since day one. We've not made any progress towards addressing them. They still plague the latest state-of-the-art models, like Claude 3.5, for instance. This is a paper from just a few days ago, from last month, that actually investigates some of these examples in state-of-the-art models, including Claude 3.5. So a closely related issue is the extreme sensitivity of LLMs to phrasing. If you change the names or places, variable names in a text paragraph, it can break LLM performance. Or if you change numbers in a formula. There's an interesting paper that investigates this, so you can check it out. It's called Embers of Autoregression. And people who are very optimistic, they would say that this brittleness is actually a great thing, because it means that your models are more performant than you know. You just need to query in the right way, and you will see better performance. You just need prompt engineering. And the counterpart to that statement is that for any LLM, for any query that seems to work, there is an equivalent rephrasing of the query that a human would readily understand that will break, right? And to what extent do LLMs actually understand something if you can break their understanding with very simple renamings and rephrasings? It looks a lot more like superficial pattern matching than robust understanding. We lost the clicker. Can you go next slide? Thank you. And besides that, there's a lot of talk about LLM's ability to perform in-context learning, to adapt to new problems on the fly. And what seems to actually happen is that LLMs are capable of fetching memorized programs, like problem-solving templates, and map them to the current task. And if they don't have a memorized program ready, if they're faced with something slightly unfamiliar, even if it's something very simple, they will not be able to analyze it from first principles the way a human could. So one example, Caesar ciphers. LLMs, state-of-the-art LLMs can solve a Caesar cipher, which is very impressive, right? But as it turns out, they can only solve it for very specific values of the key size. The specific values like 3 and 5 that you find commonly in online examples. If you show it an example of a Caesar cipher with a key size like 13, for instance, it will fail. So it has no actual understanding of the algorithm for solving the cipher. It has only memorized it for very specific values of the key size, right? So my hypothesis is that LLM performance depends purely on task familiarity and not at all on task complexity. There's not really any complexity ceiling to what you can get LLMs to solve, to memorize, as long as you give them the opportunity to memorize the solution or the problem-solving template, the program, right, that you have to run to get the answer. Instead, LLM performance depends entirely on task familiarity. And so even very simple problems, if they are unfamiliar, will be out of reach. Okay, the clicker is back. And lastly, LLMs suffer from a generalization issue with the programs that they did, in fact, memorize. So some examples include the fact that LLMs have trouble with number multiplication, as you probably know, with list sorting and so on, even though they've seen millions of examples of these problems. So they typically have to be aided by external symbolic systems in order to handle these things. There's an interesting paper that investigates how LLMs handle composition. So it's titled Limits of Transformers of Compositionality. And the main finding is that LLMs do not actually handle composition at all. What they're doing instead is linearized subgraph matching. There's another paper that's also very intriguing. It's the reversal curse. So the authors found that if you train an LLM with content like A is B, it cannot actually infer the reverse, B is A. So that's really breakdown of generalization on a deep level. And that's actually pretty surprising. Like even I'm typically pretty skeptical of LLMs, so I was pretty surprised with this result. So one thing to keep in mind about these failure cases is that specific queries will tend to get fixed relatively quickly because the models are being constantly fine-tuned on new data collected from human contractors based on past query history. And so many of the examples that I show in my slides are probably already working with some of the state-of-the-art LLMs because they failed in the past, and so they've been manually addressed since. But that's a very brittle way of making progress because you're only addressing one query at a time. And even for a query that you patched, if you rephrase it or if you change names and variables, it's going to start failing again. So it's a constant game of whack-a-mole, and it's very, very heavily reliant on human labor. Today, there's probably between 10 and 30,000 humans that work full-time on creating annotated data to train LLMs. So, on balance, it seems a little bit contradictory. Like on one hand, LLMs are beating every human benchmark that you throw at them. And on the other hand, they're not really demonstrating a robust understanding of the things they're doing. So to solve this paradox, you have to understand that skill and benchmarks are not the primary lens through which you should look at these systems. So let's zoom out by a lot. There have been historically two currents of thought to define the goals of AI. First, there's the Minsky-style view, which echoes the current big tech view that AGI would be a system that can perform most economically valuable tasks. So Minsky said AI is the science of making machines capable of performing tasks that would require intelligence if done by humans. So it's very task-centric. You care about whether the AI does well on a fixed set of tasks. And then there's the McCarthy view. So he didn't exactly say what I'm quoting here, but he was a big proponent of these ideas, that generality in AI is not task-specific performance scaled to many tasks. It's actually about getting machines to handle problems they have not been prepared for. And that difference echoes the Locke view of intelligence versus the Darwin view of intelligence. So intelligence as a general-purpose learning mechanism versus intelligence as a collection of task-specific skills imparted to you by evolution. And my view is more like the Locke and McCarthy view. I see that intelligence is a process, and skill, task-specific skill, is the output of that process. This is a really important point. If there's just one point you take away from this talk, it should be this. Skill is not intelligence, and displaying skill at any number of tasks does not show intelligence. It's always possible to be skillful at any given task without requiring any intelligence. And this is like the difference between having a road network versus having a road building company. If you have a road network, then you can go from A to B for a very specific set of A's and B's that are defined in advance. But if you have a road building company, then you can start connecting arbitrary A's and B's on the fly as your needs evolve. So attributing intelligence to a crystallized behavioral program is a category error. You are confusing the output of the process with the process itself. Intelligence is the ability to deal with new situations, the ability to blaze fresh trails and build new roads. It's not the road. So don't confuse the road and the process that created it. And all the issues that we are facing today with LLMs, they are a direct result of this misguided conceptualization of intelligence. The way we define and measure intelligence is not a technical detail that you can leave to externally provided benchmarks. It reflects our understanding of cognition. So it reflects the questions that you're asking. And through that, it also kind of limits the answers that you could be getting. It's really the way that you measure progress. It's the feedback signal that you use to get closer to your goals. If you have a bad feedback signal, you're not going to make progress towards actual generality. So here are some key concepts that you have to take into account if you want to define and measure intelligence. The first thing to keep in mind is the distinction between static skill and fluid intelligence. So between having access to a large collection of static programs to solve known problems, like what LLM would do, versus being able to synthesize brand new programs on the fly to solve a problem you've never seen before. So it's not a binary, right? Either you have fluidity or you don't. It's more like a spectrum, but there's higher intelligence on the right side of the spectrum. And the second concept is operational area. There's a big difference between being skilled only in situations that are very close to what you're familiar with versus being skilled in any situation within a broad scope. So for instance, if you know how to add numbers, then you should be able to add any two numbers, not just specific numbers that you've seen before or numbers close to them. If you know how to drive, then you should be able to drive in any city. You should even be able to learn to drive in the US and then move to London and drive in London, where you're driving on the other side of the road. If you know how to drive, but only in very specific geo-fenced areas, that's less intelligent. So again, there's a spectrum here. It's not a binary, but there's higher intelligence on the higher generalization side of the spectrum. And lastly, the last concept is information efficiency. How much information, how much data was required for your system to acquire a new skill program? If you're more information efficient, you are more intelligent. And so all these three concepts, these three quantities, they're linked by the concept of generalization. And generalization is really the central question in AI, not skill. Forget about skill, forget about benchmarks. And that's really the reason why using human exams to evaluate AI models is a terrible idea, because exams were not designed with generalization in mind. Or rather, they were designed with generalization assumptions that are appropriate for human beings, but are not appropriate for machines. Most exams assume that humans haven't read the exam questions and the answers beforehand. They assume that the questions you're going to be asking are going to be at least somewhat unfamiliar to the test taker, unless it's a pure memorization exam, in which case it would make sense that LLMs could ace it, since they've memorized the entire internet. So to get to the next level of capabilities, we've seen that we want AI to have the ability to adapt, to generalize to new situations that it has not been prepared for. And to get there, we need a better way to measure this ability, because it's by measuring it that we'll be able to make progress. We need a feedback signal. So in order to get there, we need a clear understanding of what generalization means. Generalization is the relationship between the information you have, like the priors that you're born with and the experience that you've acquired over the course of your lifetime, and your operational area over the space of potential future situations that you might encounter as an agent. And they are going to feature uncertainty, they're going to feature novelty, they're not going to be like the past. And generalization is basically the efficiency with which you operationalize past information in order to deal with the future. So you can interpret it as a conversion ratio. If you enjoy math, you can in fact use algorithmic information theory to try to characterize and quantify precisely this ratio. So I have a paper about it. If that's interesting to you, you can check it out. One of the things I talk about in the paper is that to measure generalization power, to measure intelligence, you should control for priors and experience, since intelligence is a conversion ratio. You need to know what you're dividing by. And if you're interested specifically in comparing AI to human intelligence, then you should standardize on a shared set of cognitive priors, which should be, of course, human cognitive priors, what we call core knowledge. So as an attempt to fulfill these requirements for a good benchmark of intelligence, I've put together a data set. It's called the Abstraction and Reasoning Corpus for Artificial General Intelligence, or ARC-AGI for short. And you can think of it as a kind of IQ test. So it's kind of intelligence test that can be taken by humans. It's actually very easy for humans, or AI agents. And you can think of it as a program synthesis data set as well. So a key idea is that in ARC-AGI, every task that you see, every task you get, is novel. It's different from any other task in the data set. It's also different from anything you may find online, for instance. So you cannot prepare in advance for ARC. You cannot just solve ARC by memorizing the solutions in advance. That just doesn't work. And ARC tries to control for experience because you're doing few-shot program learning. You're seeing 2 or 3 examples of a thing, and then you must infer from that the program that links the input to the output. And we're also controlling for priors in the sense that ARC-AGI is grounded purely in core knowledge priors. So it's not going to be using any sort of acquired knowledge like the English language, for instance. It's only built on top of 4 core knowledge systems. There's objectness, there's basic geometry and topology, and there's numbers, and there's agentness. So we first ran a Kaggle competition on this data set in early 2020 that produced several very interesting solutions, all based on program synthesis. And right now, the state of the art is about 40% of tests are solved. And that's very much baby steps. And that's a data set that's from before the age of LLMs, but actually it has become even more relevant in the age of LLMs because most benchmarks based on human exams and so on, they've already saturated in the age of LLMs, but not ARC-AGI. And that's because ARC-AGI is designed to be resistant to memorization, and all the other benchmarks can be hacked by memory alone. So in June this year, we've launched a much more ambitious competition around ARC-AGI. We call it the ARC Prize. So together with Mike Knoop, the co-founder of Zapier, we're offering over $1 million in prizes to get researchers to solve ARC-AGI and open source the solution. The competition has 2 tracks. There's a private track that takes place on Kaggle. It's the largest Kaggle competition at the moment. You get evaluated on 100 hidden tasks, and your solution must be self-contained. So it must be able to run on a GPU VM within 12 hours with a good CPU as well. There's a big prize to get over 85%. And then there are prizes for the top scores as well. And there's even a best paper prize, 45K. So even if you don't have a top result, but you have good ideas, just write a paper, submit it, you can win some money. And there's also a public track, which we added because people kept asking, okay, but how do the state-of-the-art LLMs like GPT-4, Claude, and so on, how do they do on the dataset? So we launched this sort of like semi-private eval where the tasks are not public, but they're also not quite private because they're being queried by this remote API. And surprisingly, the state-of-the-art on this track is pretty much the same as on the private track. That's actually quite interesting. So what's LLM performance on ARC-AGI exactly? It's not very good. The state-of-the-art LLMs are doing, most of them are doing between 5% and 9%. And then there's one that's doing better. It's Claude 3.5. Claude 3.5 is a big jump. It's at 21%. And meanwhile, basic program search should be able to get you at least 50%. So how do we know this? 50% is what you get if you assemble all of the submissions that were made in the 2020 competition, which were all brute force program search. So basically, if you scale up brute force program search to more compute, you should get at least 50%. And meanwhile, humans do like easily over 90%. The private test set was verified by 2 people, and each of them scored 97 to 98, right? And together, they can solve 100%. So, 5 to 21% is not great, but it's also not 0. So it implies that LLMs have non-zero intelligence, according to the benchmark, and that's intriguing. But one thing you have to keep in mind is that the benchmark is far from perfect. There's a chance that you could achieve this score by purely memorizing patterns and reciting them. It's possible. So we have to investigate where this comes from. Because if it comes from a kernel of reasoning, then you could scale up the approach to become more general over time and eventually get to general AI. But if that performance actually comes from memorization, then you'll never reach generality. You will always have to keep applying these one-time human-guided pointwise fixes to acquire new skills. It's going to be this perpetual game of whack-a-mole, and it's not going to scale to generality. So to better understand what LLMs are doing, we have to talk about abstraction. Abstraction and generalization are closely tied because abstraction is the engine through which you produce generalization. So let's take a look at abstraction in general, and then we look at abstraction in LLMs. To understand abstraction, you have to start by looking around, zoom out, look at the universe. An interesting observation about the universe is that it's made of many different things that are all similar. They're all analogous to each other. Like one human is similar to other humans because they have a shared origin. Electromagnetism is analogous to hydrodynamics, is also analogous to gravity, and so on. So everything is similar to everything else. We are surrounded by isomorphisms. I call this the kaleidoscope hypothesis. So you know what a kaleidoscope is. It's a tube with a few bits of colored glass that are repeated and amplified by a set of mirrors, and that creates this remarkable richness of complex patterns out of just a few kernels of information. And the universe is like that. And in this context, intelligence is the ability to mine the experience that you have to identify bits that are reusable. And you extract these bits, and you call them abstractions. And they take the form of programs, patterns, representations, and then you're going to recombine these bits together to make sense of novel situations. So intelligence is sensitivity to abstract analogies. And in fact, that's pretty much all there is to it. If you have a high sensitivity to analogies, then you will extract powerful abstractions from little experience, and you will be able to use these abstractions to make sense of a maximally large area of future experience space. And one really important thing to understand about abstraction ability is that it's not a binary thing where either you're capable of abstraction or you're not. It's actually a matter of degree. There's a spectrum from factoids to organized knowledge to abstract models that can generalize broadly and accurately to meta models that enable you to generate new models on the fly, given a new situation. And the degree 0 is when you purely memorize pointwise factoids. There's no abstraction involved. It doesn't generalize at all past what you memorized. So here we are representing our factoids as functions with no argument. You're going to see why in a bit. The fact that they have no argument means that they're not abstract at all. Once you have lots of related factoids, you can organize them into something that's more like an abstract function that encodes knowledge. So here this function has a variable x, so it is abstract for x. So this type of thing, this type of organized knowledge based on pointwise factoids or interpolations between pointwise factoids, it doesn't generalize very well. You know, kind of like the way LLMs add numbers. It looks like abstraction, but it's a relatively weak form of abstraction. It may be inaccurate. It may not work on data points that are far from the data points that you've seen before. And the next degree of abstraction is to turn your organized knowledge into models that generalize strongly. A model is not an interpolation between factoids anymore. It's a concise and causal way of processing inputs to obtain the correct output. So here, a model of addition using just binary operations is going to look like this. This returns the correct result 100% of the time. It's not approximate. And it will work with any inputs whatsoever, like regardless how large they might be. So this is strong abstraction. LLMs, as we know, they still fall short of that. The next stage would be the ability to generate abstraction autonomously. That's how you're going to be able to handle novel problems, like things you've not been prepared for. And that's what intelligence is. Everything up to this point was not actually intelligence. It was just crystallized skill. And the last stage is going to be able to do so in a way that's maximally information efficient. That would be AGI. So it means you should be able to master new tasks using very little experience, very little information about the task. So not only are you going to display high skill at the task, meaning that the model you're applying can generalize strongly, but you will only have to look at a few examples, a few situations to produce that model. So that's the holy grail of AI. And if you want to situate LLMs on the spectrum of abstraction, they're somewhere between organized knowledge and generalizable models. They're clearly not quite at the model stage, as per the limitations that we have discussed. If LLMs were at the model stage, they could actually add numbers or sort lists. But they have a lot of knowledge, and that knowledge is structured in such a way that it can generalize to some distance from previously seen situations. It's not just a collection of pointwise factoids. And if you solve all the limitations of LLMs, like hallucinations and brittleness and so on, you would get to the next stage. But in order to get to actual intelligence, to on-the-fly model synthesis, there's still a massive jump. You cannot just purely scale the current approach and get there. You actually need brand new directions. And of course, AGI after that is still a pretty long way off. So how do we build abstraction in machines? Let's take a look at how abstraction works. I said that intelligence is sensitivity to analogies, but there's actually more than one way to draw analogies. There's two ways. There are two key categories of analogies from which arise two categories of abstraction. There's value-centric abstraction and there's program-centric abstraction. And they're pretty similar to each other. They mirror each other. They're both about comparing things and then merging individual instances into common abstractions by erasing certain details about the instances that don't matter. So you take a bunch of things, you compare them among each other, you erase the stuff that doesn't matter. What you're left with is an abstraction. And the key difference between the two is that the first one operates in continuous domain, and the other one operates in discrete domain. So value-centric abstraction is about comparing things via a continuous distance function, like dot product in LLM, for instance, or the L2 distance. And this is basically what powers human perception, intuition, and pattern recognition. And meanwhile, program-centric abstraction is about comparing discrete programs, which are graphs, obviously, and instead of computing distance, a distance between graphs, you are looking for exact subgraph isomorphisms, for exact subgraph matching. So if you ever hear like a software engineer talk about abstraction, for instance, this is actually what they mean. When you're refactoring something to make it more abstract, that's what you're doing. Both of these forms of abstraction, they're really driven by analogy making. It's just different ways to make analogies. Analogy making is the engine that produces abstraction. And value analogy is grounded in geometry. You compare instances via distance function. And program-centric analogy is grounded in topology. You're doing exact subgraph matching. And all cognition arises from an interplay between these two forms of abstraction. And you can also remember them via the left brain versus right brain analogy, or the type 1 versus type 2 thinking distinction from Kahneman. So of course, the left brain versus right brain stuff, it's actually an image. It's not how lateralization of cognitive function actually works in the brain. But it's a fun way to remember it. And transformers are actually great at type 1, at value-centric abstraction. They do everything that type 1 is effective for, like perception, intuition, pattern recognition. So in that sense, transformers represent a major breakthrough in AI. But they are not a good fit for type 2 abstraction, and that is where all the limitations we listed came from. This is why you cannot add numbers, or why you cannot infer from A is B that B is A as well, even with a transformer that's trained on all the data on the internet. So how do you go forward from here? How do you get to type 2? How do you solve problems like ARC-AGI, right? Any reasoning or planning problem? The answer is that you have to leverage discrete program search as opposed to purely manipulating continuous interpolative embedding spaces learned with gradient descent. And there's an entirely separate branch of computer science that deals with this. And in order to get to AGI, we have to merge discrete program search with deep learning. So quick intro, what's discrete program search exactly? It's basically combinatorial search over graphs of operators taken from a domain-specific language, a DSL. And there are many flavors of that idea, like genetic programming, for instance. And to better understand it, you can sort of draw a side-by-side analogy between what machine learning does and what program synthesis does. So in machine learning, your model is a differentiable parametric function. In PS, it's a graph of operators taken from a DSL. In ML, the learning engine is gradient descent. In PS, it's combinatorial search. And in ML, you're looking at a continuous loss function, whereas in PS, you only have this binary correctness check as a feedback signal. And the big hurdle in ML is data density. To learn a model, your model is a curve. So to fit it, you need a dense sampling of the problem space. Meanwhile, PS is extremely data efficient. You can fit a program using just a couple examples. But the key hurdle is combinatorial explosion. The size of the program space you have to look at to find the correct program is immense. And it increases combinatorially with DSL size or program length. So program synthesis has been very successful on ARC-AGI so far, even though these are just baby steps. And so all program synthesis solutions on ARC, they follow the same template, basically doing brute force program search. And even though that's very primitive, it still outperforms state-of-the-art LLMs with much less compute, by the way. So now we know what the limitations of LLMs are. We know what they're good at. They're good at type 1. We know what they're not good at, type 2. So where do we go next? And the answer is that we have to merge machine learning, like this sort of like type 1 thinking with the type 2 thinking provided by program synthesis. And I think that's really how intelligence works in humans. That's what human intelligence is really good at. That's what makes us special, is that we combine perception and intuition together with explicit step-by-step reasoning. We combine really both forms of abstraction. So for instance, if you're playing chess, you're using type 2 when you calculate step-by-step, like you unfold specific interesting moves. But you're not doing this for every possible move because there are lots of them. It's combinatorial explosion. You're only doing this for a handful of different options. So you use your intuition, which you build up by playing lots of games, in order to narrow down the sort of discrete search that you perform when you're calculating. So you're merging type 1 and type 2, and that's why you can actually play chess using very, very small cognitive resources compared to what a computer can do. And this blending of type 1 and type 2 is where we should take AI next. So we can combine deep learning and discrete search into a unified super approach. So how does that work? Well, the key system 2 technique is discrete search over a space of programs. And the key wall that you run into is combinatorial explosion. And meanwhile, the key system 1 technique is curve fitting and generalization via interpolation. So you embed lots of data into an interpolative manifold. This manifold can do fast but approximate judgment calls about the target space. So the big idea is to leverage those fast but approximate judgment calls to fight combinatorial explosion. So you use them as a form of intuition about the structure of the program space that you're trying to search over, that you're navigating. And you use that to make search tractable. So a simple analogy that sounds a little bit too abstract is drawing a map. You take a space of discrete objects with discrete relationships that would normally require combinatorial search, like path finding in the Paris metro is a good example. That's a combinatorial problem. And you embed these discrete objects and their relationships into a geometric manifold where you can compare things via a continuous distance function. And you can use that to make fast but approximate inferences about relationships, right? Like you can pretty much draw a line on this map, look at what it intersects, and this gives you a sort of like candidate path that restricts the set of discrete passes that you're going to have to look at one by one. So this enables you to keep combinatorial explosion in check. But of course, you cannot draw maps of any kind of space, right? Like program space is actually very, very nonlinear. So in order to use deep learning for a problem, you need two things. You need an interpolative problem, like it needs to follow the manifold hypothesis, and you need lots of data. If you have only 2 examples, it doesn't work. So if you look at a single ARC-AGI task, for instance, it's not interpolative, and you only have like 2 to 4 examples. So you cannot use deep learning. You cannot solve it purely by reapplying a memorized pattern either. So you cannot use an LLM. But if you take a step down, lower down the scale of abstraction, and you look at core knowledge, the core knowledge systems that ARC-AGI is built upon, each core knowledge system is interpolative in nature and could be learned from data. And of course, you can collect lots of data about them. So you could use deep learning at that level to serve as a perception layer that passes ARC world into discrete objects. And likewise, if you take a step higher up the scale of abstraction, and you look at the space of all possible ARC-AGI tasks and all possible programs that solve them, then again, you will find continuous dimensions of variation. So you can actually leverage interpolation in that space to some extent. So you can use deep learning there to produce intuition over the structure of the space of ARC tasks and the programs that solve them. So based on that, I think there are 2 exciting research areas to combine deep learning and program synthesis. The first one would be leveraging discrete programs that incorporate deep learning components. So for instance, use deep learning as a perception layer to parse the real world into discrete building blocks that you can feed into a program synthesis engine. You can also add symbolic add-ons to deep learning systems, which is something I've been talking about for a very long time, but it's actually starting to happen now with things like external verifiers, tool use for LLMs, and so on. And the other direction would be deep learning models used to inform discrete search and improve its efficiency. So you use deep learning as a driver, as a guide for program synthesis. So for instance, it can give you intuitive program sketches to guide your program search. And it can reduce the space of possible branching decisions that you should consider over each node and so on. So what would that look like on ARC-AGI? I'm going to spell out to you how you can crack ARC-AGI and win $1 million maybe. So there are 2 directions you can go. First, you can use deep learning to draw a map, in a sense, of grid state space, grid space. So in the limit, this solves program synthesis because you take your initial grid input, you embed it on your manifold, then you look at the grid output, you embed it, and then you draw a line between the 2 points on your manifold. And you look at the grids that it interpolates. And this gives you approximately the series of transformations to go from input to output, right? You still have to do local search around them, of course, because this is fast, but this is very approximate. It may not be correct. But it's a very good starting point. You are turning program synthesis into a pure interpolation problem. And the other direction you can go is program embedding. You can use deep learning to draw a map of program space this time instead of grid space. And you can use this map to generate discrete programs and make your search process more efficient. So a very cool example of how you can combine LLMs with discrete program search is this paper. Hypothesis search, inductive reasoning with language models. So it uses LLM to first generate a number of hypotheses about an ARC task in natural language. And then it uses another LLM to implement candidate programs corresponding to each hypothesis in Python. And so by doing this, they're actually getting a 2x improvement on ARC-AGI, so that's very promising. Another very crude example that's very promising is the submission from Ryan Greenblatt on the ARC-AGI leaderboard, the public leaderboard. So he's using a very sophisticated prompting pipeline based on GPT-4o, where he uses GPT-4o to generate candidate Python programs to solve ARC tasks. And then he has an external verifier. He's generating like thousands of tasks thousands of programs per task. Also has a way to refine tasks, programs that seem to be doing, close to what you want. So this scores 42% on the public leaderboard. and that's the current state of the art. So again, here's where we are. We know that LLMs fall short of AGI. They're great at system 1 thinking, they lack system 2. And meanwhile, progress towards system 2 has stalled. Progress towards AGI has stalled. The limitations that we are dealing with LLMs, they're still the exact same we were dealing with 5 years ago. And we need new ideas, we need new breakthroughs. And my bet is that the next breakthrough will likely come from an outsider, while all the big labs are busy training bigger LLMs. So maybe it could even be someone in this room. Maybe you have the new ideas that I want to see. So see you on the leaderboard for ARC-AGI. Thank you. Questions? Yeah?
So if you follow the public state of the art, the approach appears to be kind of using an LLM to sample really lots and lots of programs, like thousands of samples based on one prompt, tens of thousands of samples. And it seems that the performance goes up, maybe if you go from 10,000 to 20,000 program samples, maybe goes up by 2%. And it didn't seem like there was necessarily a limit to that improvement, or other than like the massive amount of compute that you throw at it.
There would be. The improvement is not linear. So ARC-AGI is not difficult. I mean, for humans, it's extremely easy. If you have infinite compute, you can in fact solve ARC-AGI with brute force program search, right? If you have data center scale compute, that's actually doable. We already know that you can get at least 50% with brute force search. And of course, brute force search performance improves as you throw more compute at it. Part of the challenge is to be able to solve it with limited compute resources, right? On the public track, we don't have hard compute limits. So for instance, Ryan's Greenblatt solution is actually using a tremendous amount of compute. It's costing, I think, about 10K to 20K to actually run it in terms of API fees. So it's enormous. It's only doing 42%. If you were to just apply large-scale brute force program search, you could spend hundreds of dollars and get the same results, right?
So you think that performance, that the nature of that is simply you're just approaching in the limit brute force search over.
And by the way, I don't think, because improvement is going to be logarithmic, I don't think you're going to get to like 85, 90% like human level performance just by scaling compute. You will need more compute than is available in the universe.
Quick question, Francois. You said you think that the next breakthrough will come from an outsider, not from the big labs. But don't big labs like Google employ outside thinkers like yourself?
Yeah, so the way I see it, we used to have a pretty good amount of intellectual diversity in AI a few years ago. But the rise of LLMs and ChatGPT and this sort of arms race between the big tech companies to build the best possible LLM, that has kind of like led to an intellectual collapse where everyone is now working on the same things. And I think this is actually making progress towards AGI slower than it would have been otherwise. And I'll tell you, all the top entrants in ARC-AGI so far, they've been outsiders. They've not been like big tech labs. They've been, random people coming up with really interesting novel ideas. Sometimes these novel ideas actually echo what some of the big labs are doing. Like for instance, AlphaProof versus the currently leading solution from Jack Cole and his team. There's actually pretty strong parallels there.
Do you think there will be like an ARC-2 challenge that measures some more ambitious form of generalization, or is this going to be enough to sort of
Yes, these are very, very good questions. So I don't think the first system to crack ARC-AGI is going to be an actual AGI. I think we're going to get there before we get to AGI. So you can think of ARC-AGI not as a sufficient condition for AGI, but as a necessary condition. As long as we don't solve ARC-AGI, we do not have AGI. So it's a rebuttal to all the people who say AGI is already here. And another thing, you mentioned ARC-2. There is going to be ARC-2. ARC is a work in progress. Like I came up with it in 2019. I started working on it in 2017. It's a very crude attempt. It's the first attempt. As it came out and people started trying to crack it, we learned from that. We learned from that, and we want to reinvest these learnings into version 2. And then there's going to be version 3. And as time goes by, it's going to get more sophisticated, hopefully closer to real-world problems, and also more dynamic and open-ended. Like, I don't think a good AGI test in the long term can just be this sort of like static input-output pair program synthesis data set. I think it's going to go much beyond that. And I want to tackle the problem of open-endedness as well. So I would say one thing that I'm reasonably confident about is that if you solve ARC-AGI, it means that you have at least a decent answer to the question of how do we make machines that can approach problems they've not seen before and figure them out. So you're solving this specific sub-problem of AGI. And I think that's going to lead to tremendous progress. Like, that's, I would say, the most important problem that's blocking us from getting to AGI today.
So, and kind of in transition to our third contributed paper session, which is on causality. I know the first paper talks a little bit about experiential learning, as when babies learn and they begin abstracting concepts just by exploring the world. And I was wondering how you see that integrating into your ideas there.
Yeah, I have two kids. They're 3-year-old and 3 months old, respectively. And I think watching kids grow up is a tremendous source of inspiration for coming up with theories of the human mind. I think it's especially true between ages 1 and 2, I would say, because that's when cognition is still sort of like simple enough that you can see it in action. Past that point, it gets so sophisticated that what you're seeing is very, very difficult to see through. And before that point, it's also sort of like, sensorimotor affordances are not fully controlled. It's not quite like interesting enough, but at that point in time, it's really fascinating. And I do see things in my kids that have kind of like inspired me towards certain solutions that are applicable to art. I think humans actually, it's not like a controversial statement, but I do think humans are capable of performing few-shot program synthesis. The sort of process that you would need to solve ARC-AGI. But instead of applying it to this sort of like IQ-like puzzles, we are just applying it to completely everyday situations. Like, we set sort of like short-term goals, like you're a baby, you're like crawling on the floor, you want to get to an object. You set that goal. Then you enter this sort of like feedback loop where you know your current state, you can imagine the state you want to get to, right? You have this sort of like latent representation of your targets, and you're trying to do planning between the two. So that's few-shot program synthesis. And you're trying to execute, then you kind of like restart the loop. So I think this is very much how human cognition works on a fundamental level. Yeah.
Thank you, and thank you so much.